Hey, welcome back. This is 13.4. We're working with differentials. And the first thing I want to do is just kind of remind you of what went down in Calc 1 with regards to differentials. Um, Basically, we saw them, at least I saw them the most when I was doing u subs. So if you had x sine of x squared dx, this is inside the sine function. You do a u sub, u equals x squared, and then du equals 2x dx. That thing right there is a differential form of the derivative, whereas normally it would be du over dx equals 2x. In the differential form, all we do is kind of borrow the dx and slap it on the other side. Okay, so that's probably where you saw it before. Believe it or not, there is a whole section on differentials in Calc 1. Let's kind of revisit those issues, and hopefully this will help a little bit by looking at the pictures, okay? The differential picture. Okay, so recall Calc 1, and we had two-dimensional figures. Excuse me for one second. Continue. So imagine we have some sort of concave up type figure, and we're starting here at x and then moving some increment change in x. The difference between the heights of those 2 points is the change in y, and we're approximating change in y with the differential dy. Okay, and you get the differential of y using the tangent line. Okay, so delta y, again, that's just going to be, if this is a function f of x, it's going to be f of x plus change in x minus f of x, so the change in height of the y values, right? The dy then is just the differential form of the derivative. That's going to be f prime of x dx. Okay. One thing to notice for us is that dx and delta x are essentially the same objects. Okay, we'll treat them as if they're the same. If you watch those 3 blue, 1 brown videos on limits, they do a pretty good job of talking about all that jazz. But anyways, I don't really go too much into it. I just kind of take it for what it is. And yeah, so dx is just delta x for us. Anyways, visually, there's two differences, right? There's the difference between the original height and the new height, okay, and that's your delta y. And then there's this difference, the smaller difference to the tangent line, right? So this height here is going to be your differential dy. Okay, and you can use the differential to approximate the actual change in height. The closer you are to x, the better the approximation. Okay, so now in Calc 3, instead of having tangent lines, we'll have tangent planes. Okay, so imagine that same figure now in 3 dimensions. So the above picture is maybe a cross section of this thing. Let's orient its base at the point 0, 0. So the z-axis is kind of popping up like that, and maybe the x-axis is here and the y-axis is over here. And we want to approximate the change in the z value going from the origin out to maybe some point on the surface right here. Okay, and that change in height going from 0 to the surface is the delta z portion. Okay, we want to approximate that with a tangent plane. The problem is there's kind of now 2 differentials, right? There's a differential in the direction of x. Maybe it's this direction, this height, okay? And that height is many differential. So it's basically, if you call the surface, I haven't really given the surface a name, right? Let's say the surface is z equals f of x comma y. Then this differential part here will be the partial of f with respect to x times delta x. Okay? And then there's going to be another kind of differential in the y direction. Maybe this one goes higher. You know? Okay, so say this is then delta f with respect to y times change in y. Okay? And we basically get a tangent plane out of this. And I want to, my picture isn't going to be all that great, guys, but hopefully you'll be okay with that. I should push my this guy back a little bit. Okay, so I'm going to go blue on that, right to here. And then it's going to kind of obscure my change in y, but we'll say this little height here then is the partial of f with respect to y times change in y. Okay. So I can kind of extend that over to here. That, again, this distance is the change in y part. And then I can extend this other guy over to here. And then I'm going to have to bump on top of that, I'll put the change in y portion. Like this. And on the other side, I can kind of add in the change in x portion, which would be like this. And that, now this distance right here, which I'll put in yellow, is the differential, the total differential, basically. So there's two parts to it. There's this change in the x direction with regards to height, z. There's a change in the y direction with regards to height, z. So this will be your little dz. But the actual change in height then, I don't know what color to put that in, is this, you know, this distance here to the actual point. That would be your delta z. Okay, but it's the same idea from Calc 1. You're just approximating a change in height using derivatives. Just now in Calc 2, or rather Calc 3, it's a sum of two differentials. Okay, so again, let's write out, like we did before, the change in z and then dz. Okay, so the change in z, the actual change in height, would be the first mini differential. Or rather, this is the actual change in height. So you would go f of x plus change in x, comma y plus change in y, minus f of x comma y, and then your dz is going to be the sum of those two mini differentials. So you get a df with respect to x, dx plus the mini differential in the y direction. Okay, and then that's your total differential. I think they use z in the book exclusively for theirs, yeah, but you can use f if you would rather. Okay, you can extend this idea to then more variables and more variables. You just keep on tacking on extra differentials for the extra dimensions. Okay, let's actually do one of these where we're finding the differential. We'll look at number 4, looks hairy. And this is a 3-variable version. Okay, so I'm not going to be drawing that anytime soon. 2x plus y all over 5z minus 10y. Okay, so the total differential of w, first you have to take the derivative with respect to, well, I guess there's only, no, there are 3 variables. Okay, so first with respect to x, so you can kind of pretend this is the same as 2x plus y times 1 all over 5z minus 10y. And basically this part is just a constant, so you're just taking the derivative of this with respect to x and timesing it times this constant. Okay, so the derivative with respect to x of that first part is just going to be 2, and then times this 1 all over 5z minus 10y. Okay, and that would be times dx. Plus the derivative with respect to y. Now I'm going to have to do a quotient rule. Okay, so low z minus 10y times the derivative of the high, which is just 1, minus high 2x plus y times the derivative of the low with respect to y, which would be negative 10. okay, all over the low squared, and I'll simplify that in my next step. dy, and then finally plus the z portion. So now it's just the denominator that kind of has it in there. So I'll rewrite this as 2x plus y, a constant, times this function of z to the negative 1. So I'll be bringing down the exponent for the power rule. So I have a negative 1 times this constant, 2x plus y, times 5z minus 10y, subtract 1 from the old exponent, get negative 2, times, by the chain rule, the derivative of this stuff, which would just be 5. Okay, and then all of this dz. Okay, so let's rewrite that junk for our total differential. 2 all over 5z minus 10y dx. All of this junk will be 5z minus 10y plus 20x plus 10y. So the 10y's cancel, and you get 25. Oh, whoops, 5z plus 20x in the numerator. Okay, so plus 5z plus 20x all over 5z minus 10y squared dy, and then all this business, so there's a negative in front of it, and then the numerator I'm going to distribute the 5, so I'll have 10x plus 5y all over 5z minus 10y squared dz, and then type it all in and cross your fingers and hope it works. Okay, let's go back to the book and see where we are. So okay, so we're able to find total differentials. The issue of differentiability now is a little bit different than what we saw in Calc 1. If you remember the definition of differentiability there, we needed the limit of the difference quotient to exist for it to be differentiable. We don't exactly have the sort of difference quotient anymore. So if you recall, let's make this section 2, I guess. Differentiability. These things. So recall back then again, recalling Calc 1 stuff. Something was differentiable so long as the limit as change in x goes to 0 of f of x plus change in x minus f of x all over change in x. As long as that limit existed, then you would have kind of the derivative. And then we had alternate kind of definitions for this. As x goes to x sub 0 of f of x minus f of x sub 0 all over x minus x sub 0 equals f prime of x sub 0, that stuff, okay? So it was a difference quotient. And another way of writing it, yet another way, would have been probably like this, with a change in y over a change in x. Don't remember it off the top of my head. I'm not looking it up because I don't want to spend 3 hours looking it up. But the idea is kind of, if you take the limit as change in x goes to 0 of change in x over change in y, if that exists, that's going to be your derivative. And I think we can even do that at a point. We just put x sub 0 in there. So we could also think of this as figuring out the derivative of a point at a point. If you just plug x sub 0 in for x into the difference quotient up here. So you get f prime of x sub 0. Okay, so these are all, I believe, kind of equivalent ways of saying the derivative. Okay, so what I'm going to do is kind of take this one here and play around with it a little bit. So first I'm going to rewrite it by putting the f prime on the other side and including it in the limit. So if that's equal to 0, then it's differentiable. Let's take this thing then, and there is a method to my madness, it's going somewhere. take this thing and set it equal to epsilon. Okay. And then play around with it a little bit to solve it for, and I got it upside down, didn't I? I should be changing y over changing x. I'm sorry. Making a lot of mistakes today. Changing y over changing x, y, x, x. I know it's easier for me than you, but there it is. Okay, so I want to solve this thing for change in y. So change in y will end up equaling f prime of x sub 0 change in x, which is basically like a differential, right? And then plus epsilon change in x. And if epsilon goes to 0 as, how does that work? If epsilon goes to 0 as change in x goes to 0, then this thing, the original function is differentiable. So it's kind of another way of just writing basically this thing right here, or rather, yeah, that thing with x sub 0 in it. Okay. So if you know, epsilon goes to 0 as change in x goes to 0, then the function is differentiable. It's just like back in Cut 1, if the limit of that difference quotient exists, then it's differentiable. Okay, we want a similar definition now here with the two differentials involved. Okay, so we don't exactly have this difference quotient to work with. We have the derivative in the x direction, derivative in the y direction. Those had those difference quotients in them. But we don't exactly have that here now. So now what we do for differentiability is kind of just extrapolate this change in y expression into a change in z expression. And then instead of this one differential, we have two differentials, right? So we have f with respect to x of x sub 0 comma y sub 0 change in x, and then plus the other one, fy x sub 0 comma y sub 0 change in y. And then we're going to have there are two of these. Okay, so there's going to be a change in x version and then a change in y version, and two different epsilons. So the thing will be differentiable if epsilon 1 and epsilon 2 go to 0 as change in x and change in y go to 0. Okay? So before the function f is differentiable if epsilon goes to 0 as change in x goes to 0. Now f, or the z thing, is differentiable if epsilon 1, epsilon 2 both go to 0. When they go to 0, then delta x, delta y go to 0. Okay, right. So it's a little bit more complicated, and I'm hoping that you don't get blown away by this definition of differentiability in the book. It's really just an extrapolation of the original definition of differentiability from Cup 1, which you probably forgot. So if you've forgotten, this whole conversation is for naught. But hopefully you haven't forgot. Let's look at one of these types of problems. I'll take a nasty one from the homework if I can find one. I don't know what number it is. I'll just say it's an example. I want to show that this function is differentiable using this definition. In the homework, they do like a fill in the blank thing, which is pretty simple. But I'll show you what it looks like doing it the old-fashioned way. I think it's 35 in the book. I don't remember, but okay. So we have f of xy equals x squared minus 2xy plus y. In order to pull this off, what I want to do is investigate delta z, which by definition is just the difference between the heights going from x to some x plus change in x, and also in the y direction from y to some y plus change in y. Okay, so I'm going to work with this definition and kind of try to engineer this expression, and then I'll be able to show, hopefully, that as epsilon 1, epsilon 2 go to 0, then delta x, delta y will go to 0. Okay. All right. So anyways, I need to get fx and fy just so I can identify them and piece this thing together. So with respect to x, it'll be 2x minus 2y. With respect to y, it'll be negative 2x plus 1. Okay. Okay. So anyways, let's figure out what this delta z thingamajig is. So it's going to be nasty, but I'll have x. I'm just putting x plus change in x wherever I see x, and y plus change in y wherever I see y. So minus 2 times x plus change in x plus y plus change in y, and then minus f of x, which is x squared, minus 2xy plus y, FOIL, x squared plus 2, FOIL again. Distributing. We can simplify a little bit, right? So this x squared and this x squared are gone. That's about all I can do. Distribute the negative 2. Okay, let's see what we're getting here. There's a 2x change in x. Okay. Let's kind of remind ourselves of this thing we want to find. So we want to find the partial of f with respect to x times change in x, partial of y, partial of f with respect to y times change in y. Okay, so hopefully we're on track. So we got this guy. I'm just looking for like terms, I guess, at this point. Negative 2xy, positive 2xy, those are gone. Y and y are gone. There's 2x change in y, minus 2y change in x, minus 2 change in x, change in y, plus change in y. Okay, I need this 2x minus 2y times change in x. So there's one part of it. There's the other part. Okay. So I can rewrite those two as 2x minus 2y times change in x. Then I need minus 2x plus 1. So there's one part, there's the other. So plus minus 2x plus 1 with the change in y pulled out of them. And then I got these two other parts. One part is a change in x, and the other part is a change in y part. Okay, so the first part, change in x squared, will flip the fill. So I got change in x times change in x. And then the second part will be minus 2 change in x times change in y. So this part is my epsilon 1. Just call it epsilon 1. And this one will be epsilon 2. So you're just you're taking the actual change in z, and you're finessing it until you get this this delta z thing that we use in the definition of differentiability. And then if you could show that, so note as change in x, which is epsilon 1, and change in negative 2, change in x, which is epsilon 2, as these go to 0, then it's going to force or is it the other way around? Did I screw it up? No. Oh yeah, we want the epsilons. Yeah, so that's what I'm doing. The epsilon 1, epsilon 2 go to 0. It forces the change in x and the change in y will be forced to go to 0 as well. Okay, so then by the definition of differentiability, it is differentiable. Hence the function is differentiable. Ugh. It's a little bit on the level of annoyance of the epsilon delta proofs, but it is important to be able to kind of get your hands dirty and do this at least once. Okay, so clearly we're not going to want to go through that every time we're looking to see if something is differentiable. So what we have instead is theorem 13.4, which is kind of like the old theorem. If a function is differentiable, then it's continuous. If it's not continuous, then it's differentiable. Well, actually, that statement is more like 13.5. Okay, but let me just write out 13.4. So it's it says if f is a function of x and y where your partials are derivative, so fx and fy are continuous in an open region R, then the guys are differentiable. Then f is differentiable on that. Okay. So the point being that it's not enough just to presume. So you may think from your work in Calculus 1 that because this guy, if this guy here which is the kind of partial derivative and the change of x, and this other guy, the partial derivative and the change of y, you may think that just because those limits exist that the thing is differentiable, but that's not true. Okay, that's what they're trying to hammer into your head right here. Just because the thing has partial derivatives doesn't mean it's differentiable. Okay. So anyways, x comma y plus change in y minus f of x comma y all over change in y. So you may think these things existing is good enough for differentiability, but it's not the case. But this is not so. Okay, so anyways, the sort of next set of problems that you'll see down below, these ones where you have piecewise defined functions, these guys kind of are telling you, you know, it's not going to be the case. You're kind of experimenting in there and finding out it doesn't quite work. It's not those, is it? It's I guess they don't have one of those, or it doesn't work. Maybe it's later. Oh yeah. Oh, so this one, yeah. Maybe we should look at number 11. So they want you to show that the derivative with respect to x, use the function to show that the derivative with respect to x at 0, 0, and the derivative with respect to y at 0, 0 both exist, but then f is not differentiable at 0, 0. One thing we should note is that if something is not continuous, it's not going to be differentiable. So we'll just tack that in here as theorem 13.5. If a function is differentiable at a point x0, y0, then it's continuous there. And then the contrapositive of that statement will also be true. Okay, so if not continuous, then not differentiable. Okay. Okay, so there's that. Let's look at this problem now. So we have the function is number 11, f of xy is given piecewise. We have 2x squared y all over x to the 4th plus y squared when xy is not at the origin. And then it's just equal to 0 when xy is at the origin. Okay, so first they want you to use the limit definition to show that the thing is, it has its partial derivatives, okay, the x at that point. So first, the limit as change in x goes to 0 of f of x plus change in x. In this case, I'll have 0 for x plus change in x, comma, y minus, and then y we want as 0 as well. And then minus f of 0, 0 all over change in x. Okay. So looking at this thing, and this is our f of x at 0, 0, partial derivative of f with respect to x at 0, 0. So we have the limit as change in x goes to 0. Plug the 0 plus change in x and 0 into the function. So that first term, if you plug in that material, what you'll have? Well, you have 2 times change in x squared times 0 all over change in x to the 4th plus 0, and then minus plugging 0, 0 into this function, you just get 0. Okay, so if xy is actually equal to 0, 0, then you get 0 there. Okay. So that thing in the numerator is just 0, right? It's 0 over change in x to the 4th. Whatever change in x is, as long as it's not 0, that object will be 0. So you have 0 minus 0 all over change in x, which is 0 over change in x. No matter what change in x is, as long as it's not 0, that expression there will be 0. So the partial derivative at 0, 0 is in fact 0. It exists. Okay. Let's look at the partial derivative at 0, 0 in the y direction. So we have the limit as change in y goes to 0 of f of 0, comma 0 plus change in y minus f of 0, 0 all over change in y. So this will be the limit change in y goes to 0 of, and for some reason I wrote change in xy, of plugging 0 in for x, I'll have 0 no matter what in the numerator all over 0 plus y squared, and we're replacing y with change in y. 0 plus change in y, but 0 plus change in y is just change in y. And then minus f of 0, 0 is 0 all over change in y. So we get the same object, right? It's just the limit of 0 over change in y, which of course would be 0. So the partial derivatives exist at 0, 0. But we note that this thing is not going to be continuous at 0, 0. So remember, for continuity, at 0, 0, we need there were 3 things. We need the limit to exist there. We need the limit as xy goes to 0, 0 of f of xy to equal f of 0, 0. That statement kind of says all 3 things, right? We need the limit to exist. We need the function to be defined at 0, 0, and we need the limit to equal the function at that point. Okay, so let's see if we get all those things by evaluating, see if we can evaluate this limit. And we can approach from different directions. So along y equals x, so I just replace in the limit of the function. So everywhere at except 0, 0, the function is just that 2x squared y over x to the fourth plus y squared. Okay, and we're dealing with the limit as x comma y goes to 0, 0 of this thing. Okay. So first we're going to replace y with x. So we'll have the limit as basically x goes to 0. 2x squared y, so that would be 2x cubed all over x to the fourth plus x squared. Okay. You can factor that a little bit. Let's plot an x squared from the denominator. There's an x squared in the numerator, so you just get 2x all over x squared plus 1. That will be 0 over 1, which is 0. Okay, let's do a different approach. So along y equals x squared. And do the limit. So again, I'm going to lose my y, and I'll just have something in terms of x. So as x goes to 0 of 2x squared times x squared is x to the fourth all over x to the fourth plus y squared, which will now be x to the fourth as well. So you end up with the limit as x goes to 0 of 2x to the fourth all over 2x to the fourth, which is just going to be 1. In other words, the limit doesn't exist. Hence, the limit does not exist. Hence, the function is not continuous at that point. Hence, the function is not differentiable. Okay. So again, long story short, you can have partial derivatives, but the thing might not be differentiable. Okay, great. Let's look at these things for doing approximations. In the book, they'll probably do some error stuff. I'm more into the theoretical stuff, so I'm going to kind of skip that. But you can read that example if you want. There were similar examples in Calc 1. So now what I want to do is do a bit of approximation with differentials. So this would be hopefully our final section. Sorry if this video is a little long. Section 3. And of course I need a video quiz here too. So prox differential. So we're going to approximate change in z with dz. Okay, and let's look at the problems we're up against here. All these type of problems are the ones that are these differential types. So I move this guy over. Let's move this guy over. Move this guy down. Okay. So number 5, I have f of x comma y equals 7x minus 6y. I want to find f of 10 comma 8 and f of 10.1 comma 8.05 and calculate the actual change in height and then use the total differential to approximate it. Okay. Okay, so first f of 10 comma 8, that's pretty easy. Let's just plug in 10 for x and 8 for y, so you get 70 minus 48, which is 22. Then plug in these x and y values that have been changed a little bit, so 10.1 and then 8.05. Okay, and that's basically telling you your change in x is 0.1, your change in y is 0.05. Anyways, you can just plug that into the formula again, so you get 7 times 10.1 minus 6 times 8.05, calculator it, and you get 22.4. And then the change in z is basically just this guy minus this guy. Right? So you're going to have, let me just write that down, 22.4 minus 22. And in that case, it's 0.4 for the actual change in the height. So for the total differential dz, You need the partial derivatives, so the derivative with respect to x is 7, and then dx, plus the partial derivative with respect to y is -6 dy. Then you just plug in the appropriate values. So I'm plugging in 0.1 for dx. Remember, dx and delta x are the same thing, and same for delta y. It's the same as dy in this context. So I have 7 times 0.1 plus -6 times 0.05, and you would get 0.4 as well there. Okay. Let's make the next one our sort of quiz du jour. And we can do number 8. So this is the last video quiz and video quiz set number 4. 8 and WebAssign. We're basically doing the same process as we did above in order to kind of, okay, so number 8. The function you're dealing with, you extrapolate it or basically guess it from the thing that you're trying to get an approximation for. Okay? So they want you to approximate this 2.04 squared times 9.02 minus 2 squared times 9. So what is this? This is the f of x plus change in x, comma, y plus change in y, minus f of x, comma, y. Okay? So we can let f of x, comma, y just equal x squared y, and then we'll have our x, comma, y, the point, the ordered pair would be 2, comma, 9, and then our delta x and delta y are going to be judging from this original thing, 0.04 and then 0.02. Okay. Okay, so the differential then, the total differential dz or df, I'll just say dz, is going to be the partial of f with respect to x, so it would be 2xy dx, and then plus the partial with respect to y, which would be x squared dy. And then we're just plugging in the x, y, delta x, and delta y. So in our case, this would equal 2 times 9 times dx, which is 0.04, and then plus 2 squared times dy, which is 0.02. Okay? And then let me figure that out, and that should give us approximation of that value. I just want to make sure I got it right. So 2 times 2 times 9 is 36 times 0.04 plus 4 times 0.02. That should be 1.52. Okay, and I think that will get you through the homework then for this part. Yeah. Okay. Thank you for watching as usual, and we will see you next time.